Hello, everyone, and happy Friday. I'm honored to provide you an overview of Google's cloud platform and their breadth of services. For those of you who already have some exposure to GCP, this information will seem familiar. I plan on covering a lot of material today, so I'm going to request that you reserve any questions until the final Q&A section. Before I dive into the technical overview, I would like to dissect what makes Google's cloud platform so great. What truly makes it special? GCP is built on Google's global infrastructure and decades of technological innovation. Their cloud infrastructure is hosted in the same data centers that serve some of their biggest apps, such as Search, Gmail, YouTube, Drive, Workspace, Docs, etc. When GCP customers consider the speed and reliability of those applications, it should provide them the confidence that their apps and data will be secured in Google's data centers. While there is some parity and overlap in service offerings with their biggest competitors, namely AWS and Azure, there are several key differentiators. First, GCP offers a plethora of services such as hosted and serverless compute options, flexible data repositories and data warehouses, and artificial intelligence and machine learning tools. These services can help organizations modernize and transform their applications and infrastructure. GCP's integration with open source products and developer-friendly solutions help them stand out against their competitors. Second, GCP provides multi-cloud and hybrid cloud support for modern workloads with Anthos. An application developer can take the same containerized app and effortlessly deploy it to GCP, AWS, Azure, or their on-premise Kubernetes cluster. This solution provides a simple method for managing microservices and is unique to GCP. Third, Google's Active Assist recommendations engine proactively suggests improvements on your cloud infrastructure. This portfolio of tools is built on artificial intelligence and machine learning to simplify cloud operations. Active Assist will provide actionable recommendations such as reducing the cost of a VM or increasing performance on a VM, simplifying firewall configurations, modifying IAM roles, auto-scaling and auto-healing compute instances, identifying stale projects, and troubleshooting policies to quickly identify a problem and remediate it. Fourth, Google has built a broad ecosystem of technology partners that integrate seamlessly with their cloud platform. As you can see in this diagram, there are quite a number of companies that comprise this ecosystem, and the list of friendly integrators grows daily. Next, Google is proactively reducing their carbon footprint to achieve a sustainability goal of operating on carbon-free energy on a 24/7 basis by the year 2030. They're the world's largest purchaser of renewable energy. Considering the large carbon footprint created by data centers and the corollary effect on climate change, it is imperative that cloud service providers such as Google are doing their part to protect our environment. The last key differentiator with GCP is price. Google's aggressive pricing structure and cost-saving incentives is difficult to compete against in the market. Customers only pay for the services they use, and there are no upfront fees or termination charges. Google also offers automatic savings based on monthly usage and by pre-charging for resources at a discounted rate. Lastly, they make it easy to stay in control of spending with budgets, alerts, quota limits, and other free cost management tools. So in summation, GCP provides best-in-class security, hybrid and multi-cloud support, global availability and scalability, embedded machine learning and artificial intelligence, an environmentally friendly platform, and a culture of innovation. Google has a vast number of products and services. Someone was kind enough to compile all of them into a single cheat sheet broken down by technology. I've provided a link to this cheat sheet on the slide, and I'll share it with everyone at the end of this presentation. So in the next 30 or so minutes, I will speed through each of these services, so try to follow along carefully. No, I'm only kidding. I'm not that cruel. In reality, I plan on covering 6 topics today: security, networking, compute, storage, DevOps, and artificial intelligence and machine learning. First up is security. Google's approach to security can be summed up in 2 words: trust nothing. Their cloud platform is predicated on strong security principles such as zero trust, least privilege, and defense in depth. Applications, services, and individuals should only have access to the data that they need. Google's strong security posture is evident in their implementation of authentication, authorization, and accounting, policies, practices, and controls. In terms of privacy, Google makes it abundantly clear that you own your data, not Google. They never sell customer data to third parties. They do not use customer data for advertising. All of your data is encrypted at rest and in transit by default. They guard against insider access to your data. They never give any government entity backdoor access, and their privacy practices are audited against international standards. International standards, such as the ones depicted on your screen, from ISO and SOC on the global levels to HIPAA, FINRA, and SOX in the US, and GDPR in Europe, Google ensures their cloud platform can meet these rigorous compliance standards. Google takes a defense in depth strategy for protecting their cloud platform. They enforce and implement the highest security at each level by protecting their network, operations, identity, data, the physical servers and networking equipment in their data centers, and all of the services built atop the aforementioned levels. Customers can be comforted knowing that their resources are being deployed in a highly secured environment. In terms of data encryption, I just want to reiterate that data is encrypted at rest and in transit by default. Customers can also encrypt their data using proprietary encryption keys. Google provides a key manager to aid in the management of these encryption keys. This high level of security is represented in their Security Foundation's blueprint. Let's take a closer look at how Google security tools can be integrated to protect a customer's environment. So follow along with me. On the right is the customer's on-premise data center, and on the left is the VPC. Starting with number 1, customers can use Cloud Identity to establish a unified identity with on-prem. For example, you can federate your Azure AD domain with Cloud Identity to enable single sign-on and multi-factor authentication on the Cloud Console. 2, use Cloud IAM to create roles with least privilege access. These roles can be assigned to users, groups, and service accounts. 3, establish org-level policies such as disabling the external IP on a VM and propagate them across the organization to ensure the policies are inherited at the folder and project level. Moving on to number 4, leverage shared VPCs for connectivity and segregated network controls between projects. 5, build highly available and resilient topologies leveraging regions, zones, and subnets. 6, establish connectivity to on-prem with dedicated interconnect, cloud router, and firewall rules. 7's back on the left. Secure internet-facing applications with load balancers, firewall rules, and Cloud Armor. So Cloud Armor is Google's web application firewall that provides protection against DDoS attacks, supports IP whitelists and blacklists, enables geolocation-based controls, and provides application-aware defense for SQL injection and cross-site scripting attacks. On to number 8. Leverage the Cloud Operations Suite to collect logs, such as audit logs, network logs, and firewall logs. Over to the right, number 9. Monitor the environment with cloud-native tools such as the Security Command Center, Cloud Monitoring, Virus Total, Cloud Security Scanner, BigQuery, and Chronicle, which is Google's native SIEM tool, or Security Information Event Management tool. 10. Host resources in a service project, and then protect the service project using a VPC security control. Lastly, utilize additional network controls such as Google Private API Access, Cloud DNS, and Cloud NAT, or Network Address Translation. So by following Google's holistic approach to security, customers can ensure that their cloud environment is highly protected. Next topic is networking. Google has data centers and network edge locations all over the world. They have a presence in more than 200 countries and territories, 26 regions, 79 zones, and 146 network edge locations. Their global infrastructure provides a robust network for customers to tap into. In addition to being globally available, Google's network is also fast and reliable. Customers have the option of selecting either a premium or standard network tier, allowing them the flexibility to choose between a high performance network experience or a low cost and reliable network experience. Google has 146 global points of presence, or POPs for short, that allow customers to quickly access their infrastructure. This translates to an improved customer experience in terms of speed, consistency, and quality. So when you sign up for GCP, you're provided your own global virtual private cloud. This VPC is a software-defined network. This means you can easily deploy resources across the world and ensure seamless connectivity between them. In the example on your screen, there are 2 compute engine instances deployed across 2 regions, west and east. And each subnet is assigned its own private internal IP address space. In the case of the West region, the internal private subnet is 10.10.0.0, and it's a /26. And in the East region, the internal private subnet is 10.50.0.0, and it's also a /26. Google provides 3 methods for connecting your data center to your VPC. The first is an IPsec VPN tunnel. What it provides is an encrypted tunnel to the customer's VPC network through the public internet. It has a capacity of 1.5 to 3 gigabytes per second per tunnel, and it requires an on-premise VPN gateway. The next interconnect option is a dedicated interconnect, and it provides a dedicated or direct connection to the VPC networks with a capacity of 10 or 100 gigabits per second per link, and it also requires a connection in a co-location facility. Last but not least, we have the partner interconnect option, and it provides dedicated bandwidth and connection to a VPC network through a service provider through a capacity of 50 megabits per second up to 10 gigabits per second per connection, and it requires a service provider. All 3 data center interconnect options provide access to the VPC network, or the internal IP address space. Customers can also connect independent projects to each other through VPC peering. So in this example, we have 2 independent organizations with their own sets of projects. The organization on the left, example.com, has client computers connected to their consumer VPC network. Assuming the network admins of the respective projects allow VPC peering to one another, then the client computers in the example.com organization will be able to communicate with the servers in the SaaS.com organization through Google's internal network. Google provides numerous methods for managing incoming network traffic to a VPC. First up are the global load balancers, which consist of HTTP and HTTPS load balancers, which also supports content-based load balancing, which means you can route traffic to a particular website based on the URL. The next option is SSL proxy load balancers, which offsets the SSL encryption to the backend web servers at the load balancer level. And then last but not least in this section are the TCP proxy load balancers. Moving on to the regional load balancers, we have the internal and network TCP and UDP load balancers, followed by an internal HTTP and HTTPS load balancer. So let's analyze an example of a global HTTPS load balancer. First, we have Maya in California, Bob in New York, and Shen in Singapore. All 3 users are trying to access the website www.myapp.com. That host name is registered in Google Cloud DNS, and it maps to an internal virtual IP address of 200.1.1.1, which is hosted via a global load balancer. So what this means is that Maya in California will be able to access the service closest to her, which is the US West region, while Bob will access the backend servers in the US East region, and Shen will access the backend servers in the Singapore region, all through the same single universal namespace. And leveraging the global load balancer will ensure that the users will have the best performance possible based on their location. The next topic is compute. So if you were wondering which is the best resource to host my application, the answer is it depends. Let's examine why. Focusing on the supported programming language, which will dictate the operating system, the usage model, scaling, and the primary use case. First up is Compute Engine. It supports any programming language. Its usage model is IaaS, or Infrastructure as a Service. It leverages server autoscaling, and the primary use case is general workloads. The next compute option is Kubernetes, which also supports any programming language. Its usage model is IaaS or PaaS, which is Platform as a Service, and it leverages cluster scaling. The primary use case are containerized workloads. In terms of the programming languages for App Engine Standard and App Engine Flexible, both compute options support Python, Node.js, Go, Java, and PHP. App Engine Flexible has the added benefit of supporting Ruby, .NET, and custom runtimes. Both are considered as PaaS services. They leverage auto-scaling managed servers, and the primary use cases are scalable web applications and mobile backend applications. And last but not least in this section are Cloud Functions, which are microservices that support Python, Node.js, and Go. As a microservice, this Cloud Functions is serverless, so it can scale on the fly, and the primary use case are lightweight event actions. But wait, there's more. Customers can take their existing VMware environment and migrate it to GCP using VMware Engine. This service provides all of the hardware and licenses needed to run VMware workloads on Google's cloud platform. So for infrastructure admins who prefer utilizing VMware's hypervisor, they can continue to do so in GCP. One option for managing clusters of server instances is Managed Instance Groups, or MIGs. With a Managed Instance Group, you can deploy identical server instances based on an instance template, resize an instance group on the fly. A built-in manager automatically ensures that all instances are healthy. So if a single instance crashes or fails a health check, then the manager will automatically redeploy the instance from the template. MIGs support auto-scaling based on CPU performance, load balancing, utilization, custom metrics, or even the date and time. For example, if you want more servers during weekday business hours and less servers on the weekend, you can program an auto-scaling schedule in the MIG. Last but not least, MIGs can be deployed to a single zone or across a region. All virtual machines should be built using some form of a shielded image to ensure optimal security. Shielded VMs offer verifiable integrity by leveraging a secure boot mechanism, a virtual trusted platform module, and integrity monitoring. Google readily provides these shielded images for various operating systems to simplify the deployment of Compute Engine instances. Going a step further, CIS, or the Center for Information Security, has partnered with Google to provide hardened images built on top of the shielded VM images, coupled with their security configuration guidelines. These images are available for numerous operating systems and applications in the GCP marketplace. It is highly recommended that these images be used when deploying Compute Engine instances. At the start of this presentation, I touched on Anthos being a differentiator for Google's cloud platform. So I would like to elaborate further on this service. Anthos is Google's managed application platform that provides a consistent development and operations experience for multi-cloud and hybrid cloud deployments. Anthos can be deployed on top of your Kubernetes cluster, whether it is running on-premise or in the cloud. It consists of an infrastructure management layer, a cluster management layer, a service management layer, and a policy enforcement layer. The dashboard built into GCP provides a single pane of glass to monitor the health of the clusters and service meshes. On a slightly separate note, several months ago, Google introduced the automation of Kubernetes clusters and nodes through GKE Autopilot. With this service, Google's site reliability engineers will manage a customer's Kubernetes infrastructure using their expertise and security best practices, such as CIS guidelines. The SLA for autopilot pods is 99.9% uptime across multiple zones. Next up is data storage. The first option I'll review is cloud storage. The primary use case is unstructured data, such as images, media, and backups. Data can be stored in a bucket and securely shared with other individuals. Moving on to relational datasets, we have Cloud SQL and Cloud Spanner. Cloud SQL is good for web frameworks such as CMS and e-commerce, whereas Cloud Spanner is good for RDMS plus scale, which means relational databases that scale horizontally or vertically, HA, high availability, and HTAP, hybrid transaction analytical processing data. And the examples provided here are user metadata or ad tech, fintech, or martech. Moving on to the non-relational datasets are Cloud Data Store and Cloud Bigtable. Cloud Data Store is good for hierarchical mobile or web data, such as user profiles and game states, whereas Cloud Bigtable is good for heavy read and write operations and events, such as ad tech, financial data, or Internet of Things. In the enterprise data warehouse space, we have BigQuery, and it's good for analytics and dashboards. And then last up is Cloud Memory Store, which is Google's in-memory service. So Memory Store is a scalable, secure, and highly available in-memory service for Redis and Memcached. It's good for web and mobile apps or gaming, such as game states and user sessions. Next topic is DevOps. So I compiled this table to compare GCP's native DevOps tools with their open source or commercial counterparts. Starting with infrastructure as a code, GCP's native tool is Cloud Deployment Manager, and the open source or commercial tool is Terraform. The native software repository in GCP is Cloud Source Repositories, and a comparable third-party tool is GitHub, GitLab, or Bitbucket. For CI/CD, you can leverage Cloud Build natively in GCP, and Cloud Build can pull from Cloud Source Repositories or GitHub. And a comparable third-party tool is Jenkins or Spinnaker. For building images, you can leverage Cloud Build, which uses Docker commands, and Docker being the open source tool. For storing your images in the cloud or on GCP specifically, you can leverage Artifact Registry, which is an evolution of Container Registry. And similar tools on the open market are GitHub Packages or Docker Hub or Docker Registry. For deploying your environments, either test, dev, or prod, you can do so using GKE, Google Kubernetes Engine, and that's compared to OpenShift Kubernetes, which is the open source tool. So let's examine a traditional CI/CD process using native GCP tools. First, a software developer updates the source code of an app and pushes it to a cloud source repository, leveraging traditional Git commands directly from Cloud Shell. Next, Cloud Build identifies that code modification, which triggers the update of the image. The image is then updated to or uploaded to Container Registry. At the same time, Cloud Build uploads the Kubernetes deployment manifest or YAML file to Cloud Source repositories. That triggers another event in Cloud Build to apply the manifest to GKE. GKE will download the image from Artifact Registry and deploy a new pod with a new image. I hope this example helps demonstrate GCP's powerful DevOps capabilities. The final topic is artificial intelligence and machine learning. Google provides numerous tools to aid individuals with their AI and ML projects. Let's review some examples. Starting with the basics is Vertex AI, which is Google's new unified machine learning platform to help build, deploy, and scale more effective AI models. Vertex AI is good for accelerating data preparation, scaling data, training and experimentation, and model deployment. Next tool is AI Building Blocks, which easily adds site, language, conversation, and structured data into your applications. And it's good for deriving insights from images, translating between languages and meaning of text, creating conversational experiences, and delivering highly personalized product recommendations. And last up in this section is AutoML, which uses Vertex AI's capabilities for vision translation and structured data to train high-quality custom machine learning models with minimal effort and machine learning expertise. AutoML can help data scientists save time when building sophisticated models. In the conversational and document recognition arena are speech-to-text, text-to-speech, natural language, translation, and vision OCR. Finally, Google's Visual Inspection AI is a purpose-built, deep learning, algorithm-based model for high-precision manufacturing inspection. It can detect subtle defects at various stages of the assembly process, such as wrong, misplaced, missing, rotated, or deformed components. It can also locate tiny dents, scratches, cracks, or deformations on any kind of surface. So next, I would like to move on to a simple demonstration from Google that ties some of these services together. So I'll go ahead and switch over to my demo environment. Okay, great. So the first thing I need to do is open up my Cloud Shell. So let me go ahead and do that. We'll wait a second for this to load. Okay, good. I'm going to pop this into a new window, or a new tab, I should say. All right, let me hide the Cloud Shuttle editor up top. And then back on my main window, I want to close this terminal to clean it up. All right, now I have to establish my environment. So run a couple of commands. And then let me re-log in to re-authenticate into my Jenkins instance. Okay, great. So the environment is up and running. So for this sample demonstration, I'm going to be using various tools within GCP to demo a simple CI/CD process. First, for compute, I'm using a Kubernetes cluster that's located in the US East 1D region. This cluster consists of 2 nodes, 4 vCPUs. It has a total of 15 gigabytes of memory. Then for the actual CI/CD mechanism, I'm leveraging Jenkins, and I built a multi-branch pipeline called sample app. So within this multi-branch pipeline, there are 3 branches that it's monitoring code changes for. A master branch, a canary branch, and a new feature app branch. The new feature branch pertains to the dev environment, whereas master and canary are related to the production environment. And I'll dive into the canary release in a little bit. Next up, for my source code repository, I'm leveraging cloud source repositories. And this is hosting the source code for the 3 branches I was referring to earlier, the master, canary, and new feature, which again is for the dev environment. For my images, my Docker images that are deployed to the Kubernetes clusters, I'm using container registry. So container registry stores each version of the image. Every time I make a change to the code, it will build a new version of the image. That way, I can always downgrade to a previous version if I run into an issue. And as for the actual app itself, it's a simple web app that's providing information about the Kubernetes cluster that is hosting this app. So the top card is showing information about the backend server that processed the request. It provides the server's name, the application version number, the ID, the host name of the server, the zone is located in, the project name that I'm working on, as well as the internal and external IP addresses. And the bottom card is simply showing the proxy server that handled this request. So for today's demo, I'm going to make some very simple changes to the code and then deploy it in a controlled fashion. First deploy it to dev for testing and validation before moving it on to a canary release for limited testing in a production environment before promoting it to production. So the only changes I'm going to make are changing the colors of the cards to blue, as well as updating the version number so that we can identify that modifications to the code was made. Okay, so the first thing I want to do is perform a baseline validation of the various environments before I make any changes to the code, right? So again, the production environment is running version 1016. And if I run a simple curl command in my Cloud Shell to query the dev environment, which again is called new features, by leveraging a simple API call to extract the version, I'm getting the correct version number, 1.0.16 for the dev environment. Now I want to examine the actual pods for the production environment. Specifically for the front-end pods, right? So as it stands right now, I have two front-end pods that are serving requests, one for a canary release and one for a production release. Let me actually go ahead and scale up the production release to a total of 4 pods. So I'm going to run the command kubectl scale deployment gceme front-end production. For my production namespace, and again, I want the total number of replicas to be 4. Okay, I get confirmation that the front end was scaled. Let's actually see what's happening in real time. So if I examine the pods on the front end, here are the 3 additional pods that I requested for the production front end. And note that the original canary release, as well as production front ends, are about 2 hours old, a little over 2 hours old, whereas the new pods that I requested, it's showing that they're only 5 seconds old. So in terms of the status, I see that these containers are in the process of being created and they're not ready as of yet. Let me check the status again and confirm that they're all running. Great. So everything's up and running as of 37 seconds ago for the 3 new pods that I requested. All right, so the next thing I want to do is actually go into the source code repository where I'm going to make the changes to the code. So that's located in the continuous deployment on Kubernetes folder, and then the sample app repository. Before I begin, I just want to show you my global Git configurations. And you'll notice that I've specified my email address as well as my username as part of this configuration. In addition, the remote origin URL is specified as the cloud source repository under my project and under the repository for this demonstration. So again, let me list the contents of the sample app repository. And if I perform the same command again, typo, you'll see that the hidden Git repo is provided here. So this is the code that's required to manipulate the various branches, and it's stored in a hidden repository. So let me actually check my actual status right now, and you see that I'm connected to the master branch. There have been no changes made to the data, so there's nothing to commit, and the working tree is clean. So the first thing I want to do is let's modify the source code in the dev environment first. And for that, I'm going to check out the new feature branch. Great. If I do a git status again, just confirm that now I've moved to the new feature branch. So let's go ahead and clear the screen. The actual files that I'm going to modify for this demo are html.go and main.go. So in html.go, I'm simply going to change the colors of the top and the bottom card, right, from orange to blue. And in main.go, I'm simply going to change the version number. So while I can use a text editor, a built-in text editor in Cloud Shell, such as Nano or VI to modify the code, what I actually want to show you is the Cloud Shell editor. So the Cloud Shell editor is a graphical user interface that allows you to modify the code directly within the console. I'm going to open up my workspace for where that code resides. So it's in continuous deployment on Kubernetes. And then I'm going to expand the sample app repository. Okay. So here are the two files I'm going to modify, html.go and main.go. I also want to point out that auto-saving is enabled. So that way, as I'm making changes, they will be saved to the file on the fly. All right, so very easily, let's change the top card to blue and the bottom card to blue as well. Great, so that change was saved. In the main.go, I'm going to update the version number, change it from 1.0.16. That number represents the number of time I run this demo. And we're going to change this to version 2.0. This is a huge release. We're changing the color from orange to blue, right? So this is production. I'm making all these changes to the dev branch, or the dev environment, I should say. Okay, so now that I've modified the code, I'm done making changes to the actual files themselves. So I'll close my text editor. And let's run a, let's run a git status to demonstrate that the two files have been modified. That modification has been recognized. And now I want to add these files to the index. And I'll run a git status again to confirm that both files have been successfully added to the index. They're green now. And now I want to record these changes to the repository with a git command. So let's do git commit and add the message that I'm updating the web app to version 2.0.0. This is gonna be huge. Okay. So now I'll push. I want to push the changes that I'm making to my local repository to cloud source repositories with the git push command. So let's go ahead and run through that. So what's going to happen next is that Jenkins, which is my CI/CD tool, is going to scan the cloud source repository for any changes made to any of these branches and then build a new image based on it. So while that's taking place, I just want to point out that in the Jenkins dashboard, I can see from the weather map, right, that the forecast is sunny across my historical builds for the master, canary, and new feature branches. Everything's successful, everything's healthy, so I'm very pleased by that. Next up, I also want to show you that in cloud source repositories, let me switch over to the dev branch, which is new feature, and all right, typo here. Anyway, the dev branch, the change was committed here as well. It was added. So with cloud source repositories, I can actually view the changes to the code for each branch. So we'll see that the version number was updated here to 2.0, as well as, let's go back. I can see the contents of each modification directly through Cloud Source Repository. So this is very helpful if you need to troubleshoot code modifications that were made from a previous version to a new one. Now, I do want to point out that modifications to the files themselves, to the code, they should only be done through a source control method or version control system such as Git. So let's move back to Jenkins, and we'll see that a build is in the queue. Okay, it's running now. Let's actually pull up the console and see what's happening. So it's processing the code changes that were made. I think it actually finished. Correct. Yep, here's the latest build. It was successful. It only takes less than 90 seconds. So we'll validate the dev environment in a bit. But before I do that, I want to dive a little bit deeper into the Kubernetes cluster that I created as part of this demo. So here's my cluster that's hosting the Jenkins app as well as the actual front-end web server. By the way, let me refresh the web app to show that the changes I made have only affected the dev environment, not the production environment. So for this cluster, it consists of a 2-node pool, and here are the various specs for the individual nodes on the bottom. Next up, in terms of the workloads, we have some pods that are being deployed and pods that are being recreated. Allow me to validate that before I move on. So I want to output the pods again, this time for the new feature, the dev environment, with the app, the label app equals GC. Okay, good. So my pods are healthy. One thing I wanted to point out is that when the image was built using Jenkins and deployed to the environment, these new pods were created as of 94 seconds ago, and the original pods were terminated. So in terms of order of operations, the new pods are deployed with the new image before the old pods are terminated. So let me go ahead and refresh this. Okay, good. And this is what I was expecting to see. So we have the Jenkins application running on a single pod and the default namespace. For the dev environment, we have one backend and one frontend pod running. And then for the production environment, we have one backend for each of the Canary and production releases, and then one pod associated to the front end for the Canary release, and then 4 pods related to the production release for the front end. In terms of services and ingresses, I can see the IP addresses that are assigned to each pod. So notice how for the production environment, we have a cluster IP for the backends, for the 2 backends for Canary and production. Whereas for the front end, it's an external load balancer pointing to the single Canary front end and the 4 production front ends. Okay, so we just modified the code for the dev environment. Let's actually perform a validation to confirm that that change was successful. If I run my curl command again to check to validate the version of the dev environment via simple API call, I'm getting the expected results. It's now 2.0.0. So great. So based on this result and the fact that the build was healthy, I'm now confident that I can deploy this code to the production environment, but I want to do it slowly. I don't want to do it all at once. So that means let's deploy it to the Canary release first. That way we can have limited testing before we deploy it out to the production environment. So let's review the expected results for the production environment before we proceed. Let me output the information about the production environment once more. Okay, that's better. Let me actually look at the front ends. All equals front end. Okay, good. So again, we have one front end for the canary release, one front and 4 front ends for the production release. What this means is that when I access the website, 20% of the time, my traffic will be routed to the canary release, whereas 80% of the time, my traffic will be routed to the production release, all right? So considering that the changes to the canary release have not been made yet, I'm receiving the expected result, which is the original software version number, which is 1.0.0.16. So let's actually go ahead and make the change to the canary release before, and then test again to see what happens. So which branch am I in? I'm on the dev branch. So let me go ahead and switch over to the canary branch. Okay, great. I got confirmation I switched. And now I want to merge the code from the dev environment to the canary release. Success. Now I want to push this code from my local repository to the cloud source repositories under the canary branch. Okay, success. Now what that's going to do is that's going to trigger a new build of the image in less than 90 seconds for the canary release and deploy it to the Kubernetes environment. So let's actually see what's happening in Kubernetes in real time. Okay, so let's get the list of pods for the production namespace in my app, GCEME. Okay, this is the original state. As the build executes, we will see some pods get terminated and recreated, right? So we have some pods here that are 13 minutes old, and some pods here that are a little under 3 hours old, about 2.5 hours. If I look at my source code for the canary branch, we should see the modification that was made to app version 2.0. Let's see if that build has started yet. Here it goes. Now, while this is building, I'll pull up I'll actually connect to the console so that we can see the output in real time. So the build process consists of 5 steps, and we should see confirmation that each step is iterating successfully. Again, less than 90 seconds, if everything goes according to plan. So here we have step 1 of 5, where it's downloading the actual data or the images and verifying it. Okay, step 1 completed. Moving on to steps 2, 3, and 4. 4 is done. Moving on to step 5. Okay, success completed. Let me go back to my dashboard for this app, and I can confirm that the canary release of the software was built successfully as of less than 90 seconds ago. Now, if I output the information about the pods for my production environment, as I expected, I'm seeing the oldest canary front ends and back ends being destroyed after the newest front ends and back ends were deployed. So we have pods that were created on the canary front end and back ends as of 22 seconds ago. Right, so I'll wait for the final, looks like a final front end to terminate before running my validation and testing. And we have go. So we have a clean environment with all the pods running as expected. So now let me go ahead and run my simple script to connect to the front end, the production environment again, and output the expected results. So as expected, roughly 20% of the time, the canary front end is responding to this request and outputting the software version that's assigned to it, version 2.0. And then 80% of the time, I'm hitting one of the four production front ends and getting the original application version, 1.0.16. So a canary release is very helpful for testing software changes in a live environment in a slow method. That way, if users report issues with version 2.0, they can, or if users identify issues with this version, they can report it and notify the application developers for additional troubleshooting. So at this point, I'm confident that my software code is valid and operational. I want to now release this to production and update it so that the changes are reflected on the actual website. So almost at the finish line, let's switch over to the master branch. And now I don't need to modify any code. I just want to merge my code from the canary branch to the master branch. Success. And now I want to push this to cloud source repositories. Okay, success. All right. Roughly 2 more minutes before the Q&A section opens, once this build completes in less than 90 seconds. So have your questions ready. But while we're waiting for that to happen, let's actually see what's happening in the master branch. And I'll refresh. Great. So the master branch has been updated. I can confirm that. In Jenkins, I should see the build initiating within a couple of seconds. In addition, I wanted to point out that this environment will go back to its original state of having one backend for each of the canary and production releases, as well as one front end for each of the canary and production releases. Okay, I almost refreshed. Getting a little impatient over here, but it's building. Let's check out the console output once more. Again, it's going to run through that 5-step process. Once this completes, we'll review the pods themselves, the health of the pods, before performing our final validation test. Okay, here's step 1. Success. Moving on to step 4, correction, step 5. And mission accomplished. That build is completed. Let me go back to the dashboard. We have a sunny forecast for the master branch, actually for all 3. That build is successful. Now let's see what's happening to the pods in real time. We see all of the new pods have been deployed for the production front end and back ends. And then all of the original pods for the production front end and back ends are being terminated. So once this process completes, we'll perform our validation. Getting closer. One more to go. Okay, voila. We're back to our original state of having one backend for each of the canary and production releases, as well as one front end for both releases. So let's do our validation. Run that simple curl loop. And now I'm only getting responses from version 2.0. What that translates to is the modifications on the production website to incorporate the changes that were made during this demonstration. So that concludes the demo. We have about 4 minutes or so left. I'll open the floor to any questions.